Morning, Sir James Singh and all the participants. Welcome to the second day of the GAN course on advance in enhanced oil recovery in shale and tight reservoirs, opportunities, challenges. So today we are having, as usual, 4 lectures, and first 3 lectures will be delivered by Professor James Singh, and already 2 classes has been taken by Professor James Singh, and I am happy to share that we received good response and feedback about the classes. And today there are basically 3 lectures are there that is shared in your timetable. So now I request Professor James Singh to start your classes. So accordingly, for each class, you can take this 10 minutes break, and subsequently you can start your next class. Okay, and just I want to share that last class, that is at around 12 o'clock, I am having one class on chemical enhanced oil recovery for shale and tight gas. Okay, Professor James Singh, now it is over to you.
Right, thank you, Professor Mando, and good morning, everyone. So today I'm going to continue with the yesterday's class and to introduce some fundamental properties for the shale reservoirs. So yesterday we stopped here about we stopped at interfacial tension. So as I mentioned yesterday, interfacial tension, the unit is this unit is per length per meter, for example, in SI unit. So then it's called, this is tension. But for force, so then you simply just multiply by the length of the interface. Okay. So then let's look at this unit. Let's say an inconvenient unit is dyne per centimeters. So dyne per centimeters is exactly the same as the millinewton per meter in SI unit. These two units are exactly the same. Okay. So because let's see, we simply just this one millinewton let me simply show you. Millinewton is 10 minus 3, right? A milli. Newton is Pascal per, no, Newton should be the kg meter second, right? So then divided by meter, then become here k minus 3 is basically cancel each other. So we have a gram, and we have gram meter. Okay, now we have then meters is 100 centimeters. All right, so here's second, here is 100 centimeters. All right, so you cancel 100. Now what you get is gram, centimeters, meters, and here centimeters. Now you can see this is dyne, right? Here centimeters. Now you can see these two units we have derived are exactly the same. All right, so the first thing, unit. Second thing is, let's look at this unit again, and this unit, millinewton per meter, in the nominator denominator we multiply by meter. Okay, so now what about this one? This is force multiplied by meters or less. So what's this one is the energy, right? So this is F multiplied by meter length is energy. And here in the denominator, we have meter squared, which is surface area. So now you can see this interfacial tension unit is actually the energy unit. Okay, so therefore this sometimes we call surface tension, then we call surface energy. All right. So that is the interfacial tension. Next one is we're going to move to another one called wettability. First, look at this picture here. You have this is solid rock, and if you pour water, spread water on the surface of this rock, so what do you see? Generally, probably we say this water is just spread on the surface of rock or stick to rock surfaces. Okay, that's what you see in your daily life. But if you look at it closely, actually, let's say you have a little bit water droplet and stay on the surface. Now, if you, in case you have here is you have this is air. What you probably you experience or you see in the in daily life. But if you put such kind of solid rock in a container, and the container outside is it's oil instead of air, so then this water droplet will behave like this one. So what do you say? So this water is not completely spread on the rock surfaces. You have such kind of droplet and stand out. So in this, then this water droplet and the oil, you have interface here, right? This is interface between the oil and the water. So at this interface, and here at the solid surface and the rock surface, and you have you form a counter angle and by the water. So here, counter angle is defined from this rock surface and go to another interface. So this angle we call weighting angle. Okay, or we can use theta, and because here we measure the angle through the water phase. So generally we use called water. Theta W means water angle through the water phase. And then, of course, here you have another angle, which goes through the oil, right? So now this is theta oil. Now, from this geography, geometry, what you can see? You can see that this theta oil and plus theta W equals 180 degrees, right? So that's the relationship between the two. Then let's look at another one. Say if we change this oil to water, and we change this water droplet to oil droplet. So as the oil is lighter than water, right? So oil droplet will float. To stop the oil float, you have to put this solid on top. So then this solid or rock is going to stop oil drop float to the top or rise to the top. And similarly, then we can find this angle still goes through this rock surface, goes through water phase to another interface. So this is the counter angle or weighting angle, or sometimes we can call contact angle. So counter angle W, okay? Here is similarly, here is this side is contact angle with oil. This add together should equal to 100. Oh, no, sorry, 180, right? So here we define, how do we define the weightability? So we use contact angle to define it. Now let's move on. So here is, let's further discuss the contact angle. In this picture, contact angle is less than 90 degrees. So then this contact angle is water contact angle. So then this water, we call this one is water wet. Okay. In this, if this water contact angle, we call it this. Here is general definition. It's the wetting for that phase. That phase here is water phase. So then this is called a water wet. So in this case, called water wet. Why we call water wet? Let's say you can imagine this is have contact angle here, theta. If the contact angle is 0, that means this water droplet is completely spread on rock surface. So what does it mean? That this water is, it's common sense. You can understand this water is strongly stick to the rock surface. If the water strongly stick to rock surface, what does it mean? They like each other. So therefore we call water wet. So from this description, what you can see is, if the contact angle is smaller, it is more water wet. Okay? So that is, so then further, if the contact angle is equal to 90 degrees, so it's in the middle, right? So we call neutral wet, because if the water wet is 90 degrees, then oil weighting contact angle will be 90 degrees too. So they are contact angle, as I mentioned earlier, I just said, this contact angle represents the weighted whole wet, right? So if both water and oil are equally angled, then they are equally wet to the rod. So then we call this is neutrally wet. Then obviously it's easy to understand, if it's greater than 90 degrees, then it is oil wet. All right. So therefore, simply says we just use such kind of contact angle to determine the weightability, to describe weightability. Sometimes we do not use angle, we just use cosine theta value to describe weightability. Obviously, if the theta equal to 0, then cosine theta equal to 1. If the theta equal to 180 degrees, then this cosine theta will be -1. So therefore, sometimes we use cosine theta. This cosine theta is called what's called weightability index or weighting index. Okay, so therefore, weighting index equal 1 is completely wet. And then if it's -1, it is completely non-wet. Right. So here is some examples here. Here are some examples. And in this one, contact angle goes through the water phase is 25 degrees. So therefore, this is water wet, right? And here, this one is 80 degrees, is less than 90 degrees. So it is still water wet, but it's not as strong as case A. Now let's look at oil C, or oil C, case C. So then this contact angle is 160. So it's greater than 90 degrees. So therefore, this is oil wet. And the last one, D, then it is 35 degrees. So then this is water wet. Okay. So in the bottom line is in the bottom line. So here, first one is 25, here is 50, or here is 55, here is, so all three here is water wet, but a different degree. So of his first one is lower angle is most wet, water wet. And the last one is 105 degree, so it is oil wet. All right. Now, so let's say what is the let's go come back again. What is the meaning by wet, oil wet or water wet? First, let's look at oil wet. Oil wet I mentioned earlier. So oil, oh, I'm sorry, water wet. First, when the rock is water wet, so water film will stick to the rock surfaces. So then similarly for the oil wet, then oil film will stick to the rock surfaces. But now so far, let me ask you a question. When we produce oil, do you wish rock is oil wet or water wet? Right? So from this picture, you can see if the oil wet, where oil will stick to the rock surfaces, then it will more difficult to be produced. So therefore, look from this description, looks like oil wet is preferred. But okay, I'm not going to talk about in details about this subject, but in reality, it's not that simple. Okay, it's not like it's more it's water wet is better than oil wet. Probably we cannot have such kind of conclusion. Sometimes actually it's intermediate wet is better. So that's an advanced topic. So we leave it. We're not going to talk about this stuff anymore. Okay, now let's here is the wettability definition. Here is you could have different phases. We can different sentences or different ways to describe wettability. Reservoir wettability, okay, can be defined. First one is relative ability for a fluid to spread on a solid phase in the presence of another fluid. So what I can say is we can talk about a spread in the presence another way. So therefore, from this description, what is the condition? What's the condition for you to describe wettability? First, you have one solid. Then you have another one is one fluid. Third one is another fluid. So now to describe wettability, we need to have one solid, two fluids. Okay, so that is that's a condition, or that is set up to define the wettability. Okay, so that second definition is tendency of a surface to be preferentially wet by one fluid. So now you can see that it's preferentially relatively or tendency. Third one is tendency of one fluid of a fluid pair to coat surface, okay, spontaneously. The third one is the tendency of fluid to spread on and preferentially adhere to all wet as solid surface in the presence of the other immiscible fluid. Another definition is reservoir wettability is determined by complex interface tender boundary condition acting within the pore space of sedimentary rocks. So then next one is a term used to describe relative adhesion of two fluids to a solid surface. Last one is when two immiscible fluid contact a fluid surface, one of them tends to spread or adhere to it more than the other. So all this we can say is similar. What is the keyword here? Well, keyword is you have two fluids one solid, and they have talked about the tendency of one fluid over another one. And they talk about coating, spread, or here. So all different terms, but through all this stuff, you get some idea what is the wettability means. Okay. All right, so after we talk about wettability and infiltration, now we're going to talk about capillary pressure. So first, let's look at this right-hand side picture. So in this is here is L, or white area is L, and here this is small tube. Okay, for this this is in this picture, and the tube looks big, but for clear presentation purpose, but actually this tube is very small. So this small tube, it's so small we call capillary tube. Okay. So then here is a container, like a cup. And in the cup, we pour the water, for example. Okay, what will happen is, what we found is when you pour a small capillary tube and insert this in the water, what happens? Water goes up. Water just goes up along this capillary tube. Okay, probably some people may have had such kind of experience. When you put a small needle, so for example, in the water, so water will climb in the or go to the middle, go to this small needle or small tube. Okay, small tube. Now, okay, so that's I'm sorry, I forgot. So it's probably let's have a break first, then we'll come back to we come back. No, I'm sorry, it's not yet. All right, this timing is different timing. I'm always confused. Okay, let me continue. I'm sorry. So let's say now first. So this is the phenomenon. You see the water climbs in the tube. And what is, so because of this, let's see now, water surface is climbed in the top, right? It's so high. So then, let's say, look at this interface. Here above is L, and in the bottom is water. In the bottom is water. Then next question is, what about the pressure in the L and pressure in the water is same or not? Here we have PA, here we have PL, L liquid. Let's say in this example where you see water, or we just generally see liquid. So my first question is PA equal to PL or not? Okay. Let's analyze forces. Here is L, right? Here is L, but here is also L. So now this L pressure at two locations should be same, right? Because L is so light, and we can ignore the gravity. See, we can assume here is L is same. Okay. But now let's look at here. This is water phase, right? So this air pressure and should be close to the water pressure it should be equal to water pressure at the surface. Okay, it's flat. All right, so this water pressure here is same depth, same depth, same level. So then this pressure must be same, right? Here is PL, here is also PL. These two liquid pressure should be same. All right, but then here we have another PL in the top. But now you have water column, and obviously, so this pressure in the top and pressure in the bottom should not be same. Why? Because you have water column. Water has gravity. So therefore, this in the bottom, water pressure should be higher than water pressure in the top, right? Okay, so therefore, but this water pressure equal to air pressure. So then this pressure should be lower than, this liquid pressure should be lower than air pressure. You see that now? So therefore, at the top, this interface, the pressure at the two sides of the interface are different. And the pressure in the liquid phase is lower than pressure in the air phase. Okay, that's the, so what now here we see, we said by the analysis, we found these two pressures are different. But then in the earlier, we assume pressure in the bottom top flat surface, we say air pressure equal to water pressure. Okay, so that's we assume. So therefore, what is the difference between the two interfaces? When in the bottom is flat interface, then in the top, it's curved. It's not flat surface. So then from this description, what I can say, so capillary, this is the capillary pressure. At the top, you have such kind of non-flat or curved surface. And at the curved surface, the pressure at two sides of the curved surface are not same. And later on, we're going to talk about more. I'm going to come back to explain why the curved surface, the pressure is different, and but for flat surface, pressures are almost same. Okay. Before that, let's define what is capillary pressure here. Okay, because we have a difference in the pressures at the two sides of curved face, right? So this difference, okay, in this case is P air pressure minus P liquid pressure, because they're different. They are different, right? So we call this difference is called capillary pressure. Here we call this is capillary pressure. And then let's move further, make a more general definition. So in this case, air and liquid, in terms of this tube, which is the waiting phase? Which is the waiting phase? For waiting phase, let's check the contact angle here then. Now, this is interface, right? You go through this way interface, and here is a solid surface. And let's look at this is the water phase. What is water angle? Water angle is through this interface and goes through the water and touch the solid. So now we have this theta. So this angle is same. We call this is the angle, cosine theta. I mean, this is theta. You can see that this theta is less than 90 degrees, right? See, now you can see, so therefore, this is liquid is waiting phase. So therefore, this for this capillary tube or small tube, it is liquid waiting. Or in this case, let's see if it's water, it's water waiting. And here, then what about the air? Then air will be non-waiting, right? Will be non-waiting phase. Okay, so then what is the capillary pressure? We use PC. Capillary pressure equal to PA minus PL. So PA is non-waiting phase. We use NW. And liquid phase is waiting phase. So now we can move this definition to a more general definition. The capillary pressure will be non-waiting phase minus waiting phase pressure. So that is definition of capillary pressure. All right. Now let's further analyze the force acting on this small tube. First, let's analyze this water column. And we choose the water column as our object of analysis. Okay, then we analyze how many forces acting on it. First, it must have gravity, right? Okay, it's called it's have gravity. What is gravity? You see, let's use it. Let's simply use the WG, water gravity. And we have interfacial tension here, right? We mentioned earlier at the interface, there is interfacial tension. This interfacial tension here is, let's say, F sigma. Okay, interfacial tension. And then, so then we must see. So first, then interfacial tension with gravity, and then let's say that's the two forces acting on it. So then, what is doing to interfacial tension? What is the force? What is the magnitude or value of the interfacial tension? So this one should be interfacial tension sigma between the air and liquid, and we mentioned that the interfacial tension is this sigma is per unit length. So what is the whole long of this interface? Is we have 2 pi r. See, because you have here you have this circumference, right? So therefore, what's the value of circumference is 2 pi r. So that is total length. Total length multiplied by in sigma, that is total force here. But if we analyze the force in the vertical direction, and this vertical direction must be multiplied by cosine theta. Okay, that is here. No, so that is force here, vertical direction. And then what is gravity? Gravity is simply just this gravity, right? This column should be rho g. What is volume? We have, what is volume? Volume here will be 2 pi. Okay, volume, I'm sorry, not 2 pi. Is pi r squared, that's the area multiplied by the height. So that is total volume multiplied by rho, that become mass, multiplied by g, gravity constant, will be the gravity force. So these two forces must be equal when this water does not move anymore, right? So now we get this condition. At the end, we have this condition here. We have this relationship. What is this relationship shows? This h, to how high water will rise, will depend on interfacial tension, contact angle, and this radius. Okay, this radius of the small tube. Radius of the small tube. Now, let's further talk about this radius r. Okay, in the previous slide, I mentioned the interfacial tension, capillary pressure exists at this curved interface, but not at a flat surface. Why? At a flat surface, what is R? At a flat surface, we can imagine this flat surface is a curved surface, and when R is very large or infinitely very large, this curved face will become a flat face, right? So therefore, at this flat surface, R is infinitely large, very large. So then let's look at this relationship between the H and R. If the R is very large, what about H? H is going to 0. So that means water will not go up. So that's why So if the water does not go up, so then at the interface, what about the PC? PC must be 0 because there's no water cannot go up. Why water goes up? Because you have interfacial tension. If the interfacial tension, then the capillary pressure depends on interfacial tension. Then if the interfacial tension is 0, then capillary pressure is going to 0 because H is 0, and then capillary pressure is 0. And so therefore, at the flat surface, there's no capillary pressure or no or interfacial tension. Okay. So then, well, I'm sorry, I'm sorry, not interfacial tension, no capillary pressure, but still have interfacial tension there. Okay. So now let's look. So let's further look at this one here. PC. Let's go back to PC definition. PC is non-wetting phase minus wetting phase. In this example, is non-wetting phase is L minus liquid. Okay. And then what about PA? PA should be equal to this. Let's say, look at this PA. PA should be P well, P liquid plus rho GH, right? Because that's the static gravity, static column or water column. So then what do they put this one into the definition of PC? So this one PL cancel. What do you say? PC equal to rho GH. So then therefore when H is 0, PC is 0. All right, so then let's look at it. So therefore we have this relationship, PC equal to rho GH now. What is H? We put H here. H equal to 2 sigma cosine theta rho GR, right? So, okay, so therefore we have rho GH. We put here is 2 sigma AL cosine theta divided by R. So then rho GR. So we cancel these two. What do we got? What are left is PC equal to sigma cosine theta R. Okay. So now we got another relationship. So this relationship determines the PC and the interfacial tension for radius counter the angle. Again, you can say when the at a flat surface, I is very large, so therefore PC is approaches to 0. Okay, so that shows very important to say is because of this kind of water wet or liquid will climb or rise at H. How to get H? Get this direction. How to get a PC? You calculate this, you use this equation. All right. So this is the air and the liquid. So similarly, we can define in oil reservoir, we are more interested in oil reservoir, right? Oil reservoir, you have oil, we have in the bottom, we have water. So now in the oil reservoir, this capillary tube is very small because pores, right? The pores very small. So it's kind of, it's same as what we describe, what we talk about, about this capillary tube or small tube. So therefore each pore will work as the capillary tube. So then this water will rise in the pore or in the capillary tube, right? So therefore, in the real reservoir, and we could understand this water some water will goes up, some water will goes up around the tube. So then next question, so we're going to follow the same method. We can define what is the capillary pressure between the oil and water and the relationship with the other parameters. So I'm not going to spend time to derive it. Basically, we can approach the same method we derive for air and water, we can derive the capillary pressure between the oil and water. So finally we got is, this is capillary pressure, 2 sigma cosine theta r. So the form is exact same, okay? The form is exact same. But the only difference we have to consider is when in this case we have to consider buoyancy, okay? Because this this is the water in the oil. Water density, oil density are very close. So then when the one fluid in another fluid, this fluid you have such kind of buoyancy. Okay, so like a boat in the river or in the lake, while boat does not sink because you have a buoyancy, right? So because water has such kind of buoyancy to support to this boat. So therefore we have, so only difference is because in the previous air and water case, air density is much smaller than water. So buoyancy is proportional to fluid density. If the air density is too small, we can ignore it. But here, oil density cannot be ignored because almost similar to the water density. So we have to consider this buoyancy. So the only thing, when you analyze the forces, we need to add a buoyancy. So simply say is, if we same again, we use this water column as object for analysis. We have water, wet, we have interfacial tension, and we have buoyancy. You just add another one is we have a buoyancy. Okay. So by then you analyze, make some arrangement, you will find this relationship. And we have another relationship is we found PC is equal to rho GH. Okay. What in the air or liquid case, what have we said? PC, air, and liquid, we get rho GH. Okay, but this rho is water, right? Okay, but here now we have delta rho. What is delta rho? Delta rho is equal to E rho W minus rho oil. So therefore, the only difference here is rho, but here is delta rho in the case of oil and water. And then we can even make these two equations consistent. Now this rho W, right? We can for the air and liquid case, we can write rho W minus rho air. GH. Because this is close to 0, so therefore this delta rho is close to rho W. Can you see that? So in other words, so in general case, we can see PC is delta rho GH, or can be calculated 2 sigma cosine theta R. So that is the equation. These two equations you need to remember. Okay. So therefore, this is describing the capillary pressure. Now let's come back to this equation again. This equation, it shows capillary pressure is inversely proportional to R. Okay, so if R is smaller, then capillary pressure will be higher. Let me further to clarify. So in this equation here, R smaller, PC will be H is higher. That's the analysis. That's observation we can make, right? We can make. Let's see. That's exactly shown here. Now let's show see this picture. Here is the same angle. but here is R is smaller. R1 is smaller than R2. So then what about height? H is higher than 2, right? Okay. So now let's look at this. Let's look at another counter angle. When the counter angle is larger, what about PC is smaller or larger? Counter angle cosine theta is the counter angle larger. This one should be smaller. If it's smaller, what about H? H will be lower. Okay. So now look at here. This angle theta 1 is smaller than theta 2. So then PC will be smaller, no, larger than PC2. Then H1 will be larger, higher than H2. Okay? So let's summarize why do we want to talk about this one? So this one, because it shows in the reservoir, you will have different radius pores, right? Some pores are larger, some pores is smaller. So then what you can see from this description, what you can see, different pores, water height will be different. And in reservoir, different location, wettability will be different, right? So then at different locations, water column will be different, or water height will be different at different locations. So that's why we want to talk about this capillary pressure and what the capillary pressure relationship with the other parameters. So now let's have a break, and after break we'll continue this with the capillary pressure. We'll come back in 10 minutes. Okay, so your time is 10 o'clock.
Hey, हेलो भाई नहीं सुनाई दे रहा है अरे सही नहीं बोला
Wait for some minute. He is not in chair. Okay. Probably has taken the leave because it's 9:50, no?
Yes, ma'am.
Break is there. He is back. Okay. Hello, Professor Sam. Do you want to take a break for 10 minutes?
I'm sorry, I already told student to have a break 10 minutes.
इसमें नहीं आ रहा बाकी तो ठीक
We'll come back in a few minutes, or 5 or 6 minutes, something like that. So student did not know that?
Sorry.
No, I told the student to have a break, right? Because the kind schedule, we have 10 minutes break now.
Yes, you may take break if you wish.
Yes, we're going to have break.
Okay, okay, okay. It's okay. So I'll be back at 10 o'clock, right?
No, we come back, yeah, about 10 o'clock, yes.
Okay, okay. Thank you. So I may take break for 10 minutes.
Hello? Okay. No, you can see my picture screen, right? Okay. If not, let me
Yes,
know.
your screen is visible. Yes.
Okay. All right. So we just described the capillary pressure changes with the interfacial tension, pore radius, and contact angle. And then from this description, we can see that different locations, the water height will be different. So then now let's look. Let me schematic show you something. Let's look at this bottom. In the bottom, it's just at the flat surface. Let's say in this below this surface, here's all water, right? So therefore, water saturation is 1. Clear? All right. Now let's move up a little bit here. Let's move to here, this level. Here is H1, here is H2. H2. Water saturation, water saturation. Now its water saturation is less than 1, right? Because here is oil, here's oil, here's oil, some oil there. Okay. Now let's further move. Move to this location. Let's say here is 2, here is 3. Now at what about S3? Is lower than SW2, right? Okay, now let's look at the top. This top, H4. What about this saturation? Water saturation. Water saturation here, you see, is almost all the oil. But you see, water saturation equals 0? No. As we mentioned earlier, during the oil reservoir, initially we have water there. Oil came here and displaced the water out. So then but oil cannot completely displace water out. So therefore, oil reservoir, you still have what? SWC. Okay, so in the top, you have water saturation SWC. Now from top to the bottom, water saturation from SWC, SW3, SW2, SW1 which is equal to 1. All right, so now what is it? So therefore at different depths, water saturation will be different. And we mentioned earlier at different depths, capillary pressure will be different, right? So therefore, in general, your capillary pressure and saturation will have such kind of relation. Let's say water saturation is high, capillary pressure is low. Water saturation is low, capillary pressure is high. In between, you have such kind of capillary pressure curve. Now it's clear? So in other words, generally SW is higher, PC is lower. So you have such kind of a curve. This is called PC curve. And then let's further look at it. When the saturation, water saturation is 100%, now up to at this 100%, because in here is 100% water, 100% water, and the capillary pressure is 0 now, right? Because only water phase is there. There's no two, if you have a capillary pressure, you must have two phases. Why? Because capillary pressure is defined by the difference of two phase pressures at an interface and at an interface. So here's capillary pressure 0. But now when you move up, this saturation is starting to reduce now. Water saturation starts to reduce from 100% to low value. So now we have minimum saturation, minimum pressure. This pressure is called a threshold. This is called a threshold pressure. Okay. So then what is the physical meaning of this threshold pressure, or PD? What's physical meaning? Now you think about this one. Initially, reservoir is fully saturated by water. Then oil come in, start to displace water out. So now you go to this direction. So water saturation is reduced. Then oil saturation will increase. So then just at this minimum pressure, so oil start to displace water out. So therefore, in other words, for oil to come into reservoir, it must overcome a small or minimum capillary pressure or threshold pressure, so that oil can come in the reservoir. Okay, and then you need more and more coming here, and then up to here, then later on, then water cannot reduce anymore. Then even you have very high pressure to push oil into reservoir, and no further oil could come because this water is irreducible water saturation. Okay, it's clear? All right, now let's go. This is general description about capillary pressure. Let's look at the shale reservoir capillary pressure look like. First, let's review for relative permeability we mentioned yesterday. And so you have a very large water saturation. Water cannot, or let's say this is a gas, water cannot flow. So also you have very large gas saturation and the gas will not flow. We have this permeability gel within this intermediate range, and the water, no water, no oil can flow. No water or no gas can flow. I'm sorry. In this picture, we show, in this picture shows the oil and water and gas phase, gas case. Okay. So then let's look at capillary pressure. Capillary pressure mentioned earlier here. This is capillary pressure curve look like for conventional. Okay. So now, but very small water saturation, capillary pressure start to increase, but then as the water saturation increase, go this direction, capillary pressure going down, okay? So then we can see, and in this is this conventional capillary pressure. But in shale, what is the problem with shale? Shale is R is very small, right? Pore radius is very small. So therefore, compared to left here, we schematically we show this capillary pressure is higher than conventional rock capillary pressure, because for shale reservoir, pore radius is small. Okay, so then now so this starting to be here is a small pressure, and then gas starting to come in and goes up. Okay, so but then what do you see here? Because in this area, no fluid coming in, right? So therefore, so this area, there's no fluid. Then there's even your within this region, no gas can be produced, no oil produced. And then if the water saturation start to decrease to this region, water saturation start to come to this region, gas saturation increase, now we start to produce the gas. So in other words, for shale reservoir, what I want to emphasize is the capital pressure is higher than capital pressure in a conventional reservoir. Right? That's what I want to emphasize. Now, next, let me give you some examples. In example one, in water and oil reservoir, the pore diameter is 4 micrometers. Counter angle 60 degrees. And how much is the capital pressure? So we mentioned earlier, capital pressure has a relationship with the interfacial tension, R, counter angle. Okay, but this problem did not give us the interfacial tension. So then what is here is water oil reservoir, right? So in other words, what is the interfacial tension between oil and water? And then in case of we do not have data, what we can do? We generally then if we do not have data, then we use typical data. So that is engineering approach. In real life, in real project, sometimes we do not have all the data we need. So what we can do then? Then we have to use the typical data. So typical data for oil water interfacial tension is 25 millinewton per meter. So then we put a 25 here, 60 degrees, and millinewton per meter. Here is radius is R because diameter is 4. So then we change it to meters, 10 minus 6. So then what do we got? We got is 12.5 kPa. That is 12.5 kPa capital pressure. Now let's give you another example based on the previous example. Well, what are you asked to do? You are asked to calculate how high water will rise above water oil contact. Okay, so all right, so this above water oil contact. Now, I have not mentioned water oil contact yet. Okay, let's come back to, let me add it. So what is oil water contact? See, this so here is the oil water contact because above you have oil, below you have water. Okay, that is called oil water contact. So then let's say how to calculate height then. Again, I ask you to remember for capital pressure has such kind of relationship with height. Right? This height PC, so PC will, from previous example, it is 12.5. What is delta lu? Delta lu is 1 minus 0.85. Okay, so then lu G here is G. Okay, so then we got finally what do we have here? 12.5, and here is 0. Okay, here should be 80. Let's use 0.8. Gravity is density is 0.8 for easy to calculate purpose. So this one is simply 0.2, and here 0.2 multiplied by this one. So you do some calculation, approximately is 6.25 meters. Okay. So what do you say? From these two examples, you can see if the pore diameter is 4 micrometers and the water column is about 6 meters. Yeah. So that is I plan to introduce about this fundamental parameter, because this fundamental parameters so far we discussed so far will be used in the next day's lectures. Yeah. Now, next one, I'm going to present talk about how we produce oil from shale reservoir. Okay. Let me pull out the presentation materials. Let's go back. Let's use. Okay, I'm sorry. Somebody ask question and see what is the content. Okay, all right. So that is. I'm going to share this screen. Share. Okay, everybody can see my screen, right? We are going to go to the next lecture. It's about introduction to oil recovery. First, let's look at this picture. First, talk about why producing shale or oil, why we produce oil gas from shale reservoir is important. First, let's look at the left-hand side picture. It shows the U.S. dry natural gas production from 2004 to 2018. And it's about shale gas. Data is 2019 EIA data, Energy Information Agency, EIA. So U.S. agency. Now, look at here. This, it's the billion cubic feet per day. And this year, as say from 2004 to 2018, and here is different colors represent the gas production from different basins, okay, different basins. And above is conventional reservoirs. So this bottom colored one are shale gas reservoirs. So what you can say? Now we can see gradually or more and more shale gas production from, or more and more gas production from shale reservoirs. Okay, by the 2018, and 70% of the gas was produced from shale reservoirs. So that is history. Now let's look at oil then. Right-hand side picture, oil. Let's look at the tight oil or shale oil. See, then similarly, these bottom color curves represent the oil production from shale and tight reservoirs. But then this gray top part shows the production from conventional oil reservoirs. Now you can see by the 2018, like 60% of the oil production is from shale and tight reservoir. So therefore, so therefore, how are we going to produce shale and reservoirs will become very important. So then let's look at the future. Now, prediction. From 2000, this prediction data up to 2050, left-hand side shows the oil production. So here, let's say, here is the history and right-hand side prediction. So you can see, and in the future, oil production from conventional reservoir in the bottom will be declined. It can be understood because and you do not have new big oil field, then the oil production from the existing field will decline. The overall production decline. But we have more tight reservoirs, so then oil production will increase with time. And similarly for the gas production in the right-hand side picture. So left is surface history, in the right is prediction. You can see overall production from conventional reservoirs decline, but gas production from shale reservoirs and increasing. So therefore, from both the history and future production, and we can see that so it's very important to know how to produce shale and gas reservoir. All right, now let's see. Then next question is, what is the status of the technology status to produce oil and gas reservoirs from or produce oil gas reservoirs? Let's look at this one. First one, so far, to produce oil and gas, what is the technology so far? First, we have to drill horizontal wells because we need a shale and tight reservoir. Probability is low, right? We need a high production rate, so therefore we need to use horizontal well instead of vertical well, because vertical well, that drainage area or the production capacity or drainage area is smaller. So first thing we need to use horizontal well. Then because the shale probability is low, we have so what do we need to do? We need to fracture, and even use a multi-stage fracture. So what is multi-stage fracture? Here you have many stages, and then after that, then you deplete it. So basically, it's schematically like this one. You have multi-stage fracturing. And then after that, then you're going to produce oil. Let's use oil as an example. Then oil come here. Then oil goes up. What about the pressure? Goes down. As more oil is produced, pressure is going down. Okay. So that is the technology status to produce shale and tight reservoirs. By using such kind of method, let's look at right-hand side picture here. Here is a different basin, have a different oil recovery. What's oil recovery? The percentage of oil which can be produced. So now you can see 8%, 7%, 3%. Overall, here is 0.9%. Overall, for these 20 US plays, or 1, 2, 3, 4, 5, 6, 7, about 7 basins or about 20 reservoirs, recovery factor is less than 5%. Okay, so then what is the problem? So now even we use such kind of advanced technology, we can only produce 5% of oil in the reservoir. So therefore, then how to produce additional oil or how to enhance oil production from shale reservoirs will become important or become urgent. We need to find out how to do that. Before I introduce this technology, let me introduce other terminology. So first one is called flooding. You probably heard about water flooding, gas flooding. You heard such kind of name, right? So then let's say here is the injection well. Here is production well. So injection well, you inject the water or CO2. Here, this is the oil reservoir, and the drive oil, and then oil produced here from. So now it is called flooding. So you have injection fluid from one injection well and produced fluids from another production well. So that is called flooding. Now let's look at another well. So in this case, here is a reservoir. Now it is a horizontal well, multi-stage fractured. And then initially, what do? You inject gas. Let's say you inject gas here. Then inject gas, then you stop inject, leave the well is closed for some days. And then you open the valve, you open it, oil and fluids, other fluids are produced back. Now, what you see is, all this here is same well. We use the same well to inject gas, then produce fluids. So this way, so in this case, when the gas is injected, or you could inject other fluids like water or any. During the injection, we call it is called a Huff. During the injection, it's called Huff. Okay. Now Huff. Then during the production, the French term called Puff. And here, that's why this process, because you have Huff and Puff, we call Huff and Puff. So that what is the, when we use Huff-Puff method, we only need one single well to inject fluid and produce fluids. Yeah. So that is Huff-Puff. Now then I skip this one. Okay. Let's say let's look at the next one is how much oil increase can we, how much oil production can be increased by Huff-Puff or by gas flooding. Let's say first look at Huff-Puff gas injection. Yeah. Before that, let me say, okay, Huff-Puff gas injection. I can skip this one. Let's look at this one too. First, what I show you some simulation results. In simulation results, I just use the one small element, and this is a horizontal well. Here is horizontal well. This is one well here, another well here, and so we talk about Huff-Puff first, right? For Huff-Puff, only need one well. Okay, then we just forget about this well. Let's say you only choose one well. So you have one well here, and then you flag. This is one horizontal well, and you flag. This is a fracture. Yeah. So then if you schematically, it's 2D, it's like this one. So here we have, this is one well here. Let's forget about this one. And here is fracture. No, sorry. These two fractures here. Now here, what is this one? It is a half fracture here. This is a half fracture. Now this is another half fracture. So add this in this model, add together, actually we simulate one fracture. Okay? We simulate one fracture. All right, so then you have, well, let's say you have one half well here. Another side, one half well here. So we add together is one well. So in simply, what I want to say is, in this model, I just use very simple model. and we simulate one well producing from one fracture. And then in real life, we'll have multi-stage fractures, right? So then we just assume production from one fracture is from different fractures same. So then if you have multi-stage fractures, the total production from this well will be multiplied by so many stages or so many fractures. Okay, so that is the methodology simulation I'm going to talk about. But later on, I can talk about more about simulation approach. Okay, here is some parameters. Reservoir properties. It's the base model. We have initial pressure 6,425, velocity 0.06. You can see that now velocity is low, right? Initial water saturation 0.3, compressibility, and shale matrix permeability. Now you can see 100 millidarcy. Temperature, gas gravity, thickness, bubble point pressure, well production pressure, injection rate. Okay, that is the model parameters. Let's see what kind of results from the model. First, let's look at gas injection, Huff-n-Puff gas injection. First, talk about the 10-year primary. I mentioned a few minutes ago. Current technology to produce shale reservoir is horizontal well, fractured, and primary production, right? So now this model shows from primary production for 10 years, only produce 5.75%, which is inconsistent with the practice average. Okay. Then we do the 20-year flooding. This flooding is gas flooding. We talk about gas flooding, Huff-n-Puff, right? So now we get an incremental 2.39%. But if the Huff-n-Puff 20 years, we get a 16.69%. All right. So what are you seeing now? Clearly, Huff-n-Puff production produce much more oil than gas flooding. So gas flooding. That's observation we see from this simulation results. Let's look at our water production. Similarly, primary is about 5.75, same as the gas modeling. And here, gas 20 years water flooding is 1.86. 20-year Huff-n-Puff is 2.4. Okay. So first, what do you say? Huff-n-Puff water flooding is still better than water flooding. But compared to the same method, different fluid, so gas recovery is much higher than water. Gas injection. Gas flooding, oil recovery much higher than water flooding. In other words, gas injection is better than water injection. Okay, so therefore, based on this simulation results, we can see Huff-n-Puff is good method for shale. And why? So next one, I'm going to explain why Huff-n-Puff is better. First, gas flooding. Gas breaks through fractures. So if you have two wells, and between two wells you have fractures, then whatever gas injected from one well will be easily break through to another well. Once gas is break through, then almost gas will bypass oil, then oil recovery will be very low. Okay, so that's the first thing is. What about Huff-n-Puff? Because you're single well, and then there's no breakthrough issue. And then you can quickly get response. Because when you when you do the gas flooding, you need to drive oil from the injection side to the production side. But for the Huff-n-Puff, once you stop the gas injection and you produce, you have puff period of time, then you immediately you can produce oil gas. So then another thing is you can cycle gas, you can inject gas you can cycle gas injection of the produced gas. So whatever gas produced, you can use to re-inject. Okay, and then if you have a fracture, actually helps, because if you fracture, then it's easier for gas quickly, for the injected gas quickly penetrate into deep matrix, and then increase of facilitating oil gas mixture. So that's the reason, and Huff-n-Puff is better than gas flooding. So then this is from common sense or from logic. Then let me use, then next thing I'm going to use the pressure data, pressure distribution to explain why gas flooding is not going to work as good as well as Huff-n-Puff. So now let's look at here. This problem, this is about pressure distribution. Here is pressure, red one, high pressure, blue one is low pressure. Now in the beginning, this is in the beginning, pressure is it's about 6,000. So then you're starting to, let's say, primary depletion. Okay, now after primary depletion, 10 years, what do you say? Reservoir pressure becomes very low. Okay, so that's one reason. And primary recovery is very low because your pressure suddenly quickly declined. Let's say gas flooding. You're starting to inject gas from left. Now left pressure increase. In the right-hand side, the production side, right? Production well. So production well, reservoir pressure is low. Now after 50 years, even 70 years, what do you say? High pressure still has not reached the middle of the two wells. In other words, so even less than half, 50% of the reservoir area is still not in high pressure after even 70 years. Why? Because shale reservoir is very tight. So pressure propagation is very slow. That's why the gas flooding does not work. Okay. Similarly, for the oil saturation, red one means oil saturation is high, so green one is low. So even though 70 years and even 50 years, let's say, look at the 70 years. So this oil production, this is in the injection side. So low pressure is less than half the volume. You still only have low pressure. But then more than half the volume still have high pressure. Oh, I'm sorry, high oil saturation. If the high oil saturation in the reservoir means less oil produced. Yeah, less oil produced. So then, so that's why the Huff-n-Puff gas flooding is not going to work. Now, let's compare what are these two here? These two compare the pressure, gas flooding, and here's water flooding. Now, what is the water flooding? You can say this green one is low pressure, and for the green one is low pressure, and red one is high pressure. For gas pressure, high pressure region is much smaller than water flooding. Why? because gas is easy to be injected. So therefore, it can increase the reservoir pressure quicker than water injection. So that's why explain why gas flooding oil recovery is higher than water flooding. Okay. Now let's look at the Huff-n-Puff case. Let's look at Huff-n-Puff case. Now in the Huff-n-Puff, this red curve shows the viscosity, and blue dotted line shows the pressure. So the green dotted line shows the oil saturation. Okay, let me first explain the pressure. Now, initially, you have primary depletion, right? Pressure is low. Okay, then you inject gas. When you gas injected, so this is block. This is pressure near injection well, near injection, near the fracture area, near fracture. So when the gas is injected, the fracture pressure suddenly increase now. Okay, suddenly increase to 7,000. From in the beginning is 2,500. Suddenly increase to 7,000. Okay, then you keep increase injection and the pressure maintains high. So therefore, this is half time. Then you puff, you produce. If you produce, then immediately pressure is going to reduce. All right. So this way is puff. Okay. So now from this, so basically this is one cycle, half one cycle. That is pressure. Let's look at the viscosity. Viscosity, when the pressure is low, viscosity is high because it's kind of dead oil, right? So no gas is dissolving oil. So viscosity of oil is high. Then during the puff, injection time, during puff, then gas dissolved in oil, so therefore oil viscosity reduced. Okay? Then you suddenly produce. During the produce, then here is puff, right? During the puff, because during the puff, some gas is, because pressure is going down, so some gas escaped from oil, so therefore oil viscosity slightly increase. Okay? Slightly increase. So that's why you can see from Huff-n-Puff, so your oil viscosity is reduced actually compared to the before Huff-n-Puff period time. So therefore, one mechanism during the Huff-n-Puff is oil viscosity decreased. And suddenly, of course, what is the significant of mechanism is pressure increased during the puff, during the Huff period of time. And because you get more gas injected quickly and pressure increased quickly. And then oil saturation increased during the, so okay, let's remember these two mechanisms. The oil viscosity is reduced, pressure is increased during the Huff and Puff injection mode. Okay, so far we use simulation data to demonstrate what I have demonstrated so far. We demonstrate gas flooding better than, let me summarize. Gas flooding better than water flooding. And Huff-n-Puff better than flooding. Either gas or water. Okay, so we demonstrated that. We also explained why Huff-n-Puff mode is better than flooding mode. Flooding mode. Because Huff-n-Puff can quickly increase reservoir pressure, reduce the viscosity, and but flooding, maybe you have it takes time to drive oil to the production wells, and another one is it takes time to build up pressure because there's some distance between the injector and producers, so long distance. So then because of tight reservoir, the pressure cannot be transported easily. Okay, so that is from simulation. Next one is, you may say simulation may not represent the reality, right? Maybe, so we need to check whether we need to check in lab whether it is true. So therefore, we did some experiment to check Huff-n-Puff gas injection. Okay, so here is field. If here is a field, in the field we have horizontal well, we have multi-stage fractures. Okay, so now if we look at one fracture, what happened? So you have one fracture around the matrix, right? So therefore, what do? We use in the lab, we use one container. We put a core plug. So this is core plug. It's kind of matrix. There's no fracture in the core. Okay, but then you have a space between the core and the container, right? This yellow area, yellow space. That yellow space represents fracture because there's a space between the core and the container. We use this fracture. Then if we inject gas in the yellow area, it's kind of injection, right? So then we stop injection, let the gas penetrate into matrix, and then we open this, we produce this gas, which represents the puff. Then we can bring some oil out. So this is the schematic of the experiment. Okay, here you have, for example, we have 3 containers here. We have put 3 cores inside in the container and between the container and matrix core. We have fractures, and then this is connected to this nitrogen or CO2 gas tank. Initially we can open this valve, inject gas into this container, and then stop injection for a while. Then we open this valve and produced. Then represent the puff. Okay, so that is the experiment. Now let's look at this experiment data. Here is oil recovery. This is the cycle, number of cycles. This is first cycle, first half and a puff. And the injection pressure is 4,500 psi. And these different curves for different core plot, with different core. So this one is Eagleford, and this one is Barnett. This is Michaels. Okay. So now, first, what you can see. First, it doesn't matter what kind of which core, all shows as more cycles, more oil produced. Okay. That's first observation. Second observation, let's say from first cycle, how much oil we're gonna get? From Eagleford, we get 30%. From other two, we get 22%. So now this oil recovery is much higher than 5% from primary depletion, right? So therefore, it demonstrates Huff-n-Puff could have high production, high recovery factor. So now if you produce like more cycles, we could even maximum could get 70%. So this experimentally verify this idea works. Okay. So next one is, and that is so now it's a good time for us to have a break. And then next we're going to discuss how other factors is going to affect Huff-n-Puff performance. Let's have a break, 10 minutes break, and we come back and at 12:30. No, I'm sorry, not 12:30, at 11 o'clock. Okay.
Okay, thank you. We'll be joining.
No. Okay, we talk about a half and puff. What is the aim? Aim is end, right? But between half and puff, generally we have we stop well. So during this time, the no injection and no production. So basically, this well is shut in, and during the shut in, what happens? During the shut in, then gas is going to contact with the oil or dissolve in oil, right? So during this contact, we call soak time. So then the next question is, should we have soak time, or how long soak time should be? And based on what description, my description, what I can say, soak time is for gas to contact with oil, right? So easy to understand, if the longer contact time, then more gas will be dissolved in the oil. And then oil viscosity will be low, and then the oil production should be higher, right? But what's another problem? When you shut in the well, then it takes time. So during this time, basically no production, no injection. So you have to sacrifice some operation time. So then if you lose some production or injection time, that means you lose some revenue, right? So therefore, it can be understood or easy to understand. There may be some kind of optimum soaking time. Too long is not good. Too short, maybe not good. Okay, then let's look at what is the effect of soaking time. First, let's look at an experiment. Now, in this experiment, you have a soaking time from 0.25 hours to 48 hours. The yellow one here is 0.25. Here, top one is 8 hours soaking time. So obviously, here is the cumulative oil recovery, number of cycles, and for at a specific cycle or time, what do you say? Well, not time. At a let's say, let's look at a specific cycle. Let's say cycle 3. What do you say? So in this case, soaking pressure is the same, and soaking gas is nitrogen. And what do we observe? So soaking time is longer, recovery factor is higher. Let's see here, this one is higher, much higher than 0.25 soaking hours. But then later on, if the soaking time is greater than 12 hours, let's see this one here, then soaking time longer does not significantly increase oil production anymore. So from this picture, looks like 12 is best, right? Okay, then so that is plot. Then that is a plot we can observe. Let's change this plot into this way, in the left-hand side plot into right-hand side plot. So what difference here? Right-hand side plot is cumulative oil, vertical axis is same, but instead of plot plot the oil recovery or oil production versus number of cycles, and we'll plot versus time. Was plotted against in soaking time. I mean, not soaking time, against operation time. Okay, so now what do you say? At the same operation time, let's for example, 30 hours. What happened? Blue one is soaking time is 2.5 hours. Other one is 24 hours. Here's 24 hours. And here's blue one. This blue one is 12 hours. Okay, that is something surprise, right? At the same time, your soaking time shorter produced more oil, which is opposite what we observed in the left-hand side. In the left-hand side, at the same cycle, soaking time long is better. But at right-hand side, at same operation time, short soaking time is better. So therefore, how to explain this one? This is simply because during the experiment, where soaking time is too long, so waste operation time. Because during the soaking time, oil produced, no gas injected, so it's kind of wasted time. So therefore, at least from this example, at least we can conclude soaking time should not be too long. If it's too long, it's going to waste time. That is very important observation. All right. Next one is, we talk about the cycle effect. The Huff-n-Puff is cycling injection, right? We inject gas, soak, and produce oil. And then we repeat such kind of process. Then the question is, how many cycles can we do it? In other words, can we constantly repeat many cycles and we still get a lot of oil produced? So in other words, how much oil can produce from each cycle? Let's look at an example first. Let's look at this slide. First cycle, here is number of, first, let's look at the first one, is number of one core. Okay, we did an experiment by using 10 cores. Let's say diameter is 1 inch diameter core, and then during the first cycle, oil recovery is 12.63. During the cycle 2, we got 8.21. Cycle 3, 8.27. Cycle 4, 6.3, 5, 4.8, 4.8, 6, 3.4, 7, 3.3, 8, 3.8, 2.7. So what do you say? As the cycles, at later cycles, oil recovery is lower than early cycles. That makes sense, right? Because initially you have more oil, it's easier to produce oil. But later on, so not much oil there left, you inject gas, and you are more difficult to bring some oil coming back. So therefore, that is easy to understand or easy to be explained. So later cycles will produce less oil than the early cycles. Then next question is, in reality, how many cycles should we do so that we could get economic oil production? All right. To answer this question, I did some experiment. And I did some simulation. So what this shows, this is the oil rate at different times. Each bar represents cycle. So because your simulation, it's easy to easy to repeat many cycles, right? So I repeated many cycles, and what did it say? Now simulation results also show later cycles produce oil rate is a bit lower than the rates in the early cycles. Okay, and then this is simulation data. What about a field? This is simulation data. It's basically is let's say, what about the other people's simulation work? And Atom, their work shows in real simulation, real naturally fluctuating reservoir, economic cycles only 2 to 3 cycles. So in other words, if you repeat more cycles, it's not going to be economic. And even another paper, they talk about only 1 cycle. The first cycle is going to be economic. After that, it is not economic. The different model will show different results, but overall, because in my model, I just simply show the phenomena without an economic analysis. But their economic analysis shows only 1 or 2 to 3. So, but conclusion is, so economic cycles must be very low. Okay. Next one is, now so far we could inject gas. We inject gas. We could inject nitrogen, and we could inject methane, and we could inject CO2, right? So what kind of gas is favorable for oil production? First, some also did some simulation work, okay? So then first did experiment. So injection pressure 2000 Wolfram, and first you use CO2, nitrogen, and methane, 3. So this, and here soaking time is 6 hours for CO2 and 18 hours for nitrogen and CO1. Production is all 6 hours. That is the experiment conditions. Let's look at here. First top case column, you have CO2, nitrogen, CO1. Okay, for the core 2, we have CO2, CO1, nitrogen. Okay, both shows CO2 is best, and the nitrogen is second. Okay, so that is it does show different gas will give you different oil recovery factor. And then they did a simulation work. First did a simulated experiment work, and then did a field work. Let's look at field work. Okay, field work here is CO2. Here is C2. Now, in the field work, also including the ethane. And the second one is CO2. Third one is, and so this one is C1. Last one is nitrogen. Now this field model shows first CO2 is still better than C1 and nitrogen, but the field shows C1 is better than nitrogen. And see which one really is better, it maybe depends on the real reservoir conditions. Okay. And so that is oil rate, oil recovery. And here is the bottom curve. It also shows that, what's bottom curve? Bottom curve shows this is C1, this is nitrogen, and here is, okay, this is nitrogen, C1, here, this is nitrogen, and C1. And so it basically is a different field, and it's compared to C1 and nitrogen, and it shows that, you see, it's even different field model, you get different results. So in other words, C1, C2, it's kind of, you know, there's no general conclusion, is no general universal conclusion say which is better. But it looks like CO2 is better than either of them. Yeah. So that is the gas effect of gas. Now let's look at the some field projects, field results. So here's I did some survey and summarized the Huff-n-Puff gas injection project. So first one is 2008 and 2008. Let's look at what did I project. First column is year, which year. Second was the field name. What is the third was injected gas, half time, soaking time, fourth time, and number of wells, and here's injection rate, performance, and reference. First, what I did is I did it from the early years to later years. Then let's look at what is the performance. First, let's look at a summary performance. First, in 2008, little or no oil increase, bad gas breakthrough. Later on, the gas breakthrough at 900 feet away. Well, and gas breakthrough in 11 days, 20% oil recovery. Oil rate increased 17%, oil 20%. So what you can say? First, later years performance better because we have better understanding. We designed the project better. Second, looks like looks like some projects had gas breakthrough problem. Then you may ask why we were earlier. I mentioned that for Huff-n-Puff, we do not have gas breakthrough problem, right? But why in field now you have gas breakthrough problem? This is because in field, although you use Huff-n-Puff, you only use one well to do Huff-n-Puff, but the neighbor wells is still producing, still in primary depletion. So therefore, when you inject gas in this well, then probably it's going to break through at neighbor wells, which is non-Huff-n-Puff well, non-Huff-n-Puff wells. So therefore, you still have, in this case, we have gas breakthrough. So in other words, this gas breakthrough is gas breakthrough to the neighbor wells. Okay. So that's the first performance. Let's look at it. Here you have different gases: CO2, methane, lean gas. Okay, overall, looks like CO2 is better gas. So which is consistent with our experiment data. So that is the field projects. Okay, here's the detailed summary from these projects I have surveyed. So gas injectivity does not seem to be a problem. So in the field projects, although shale, we mentioned shale reservoir is very tight, right? Maybe it is difficult for gas to be injected because probability is too low. But field projects shows looks like injectivity is okay. And problem is gas breakthrough was observed, as I mentioned. And so project later years performed better than the early years. I also mentioned, and tens of CO2 Huff-n-Puff tests, including some large field projects, have been carried out in Chinese low permeability sandstone reservoir. Most of those tests were claimed to be successful. Some tests were in tight oil reservoir. So in other words, more Huff-n-Puff gas projects were carried out in China, which are not included into this survey. All right. Next one is talk about field test. I have another field project. So this field test is reported by the JP is in the JPT. So let's look at this case. The production increases on 15 wells indicated from 30 to 70% reserve gain. So in other words, this project is a large project in a large field. You will Huff-n-Puff gas injection will occur in many wells, but it shows 15 wells had oil production, and 32 wells in 2016 added 300,000 barrels of oil. Work was going on 100 wells in 16 areas. This is a large commercial project. And imports and output additional capital cost average is about $1 million per well. That is capital cost addition, because you have to use install air compressor. You have to use a compressor to inject gas, for example. That needs actual capital cost. The process uses associated gas. So in other words, it's basically used produced methane and some produced gas. And production response is 1 to 3 months. So this Huff-n-Puff in the field project. So after Huff-n-Puff and soak some time, then you produce. So it takes about 2 to 3 months. So looks like what is economics? You invest $1 invested at $2 net present income. So it looks like its return is 100%. Okay. So, and from this project, it has also been observed. So it will work better if formation is able to contain high pressure gas injection near the well, and the wellbore contacted the most productive rocks, and completion maximize the fraction area was a restricted zone around the wellbore. So that is the, in other words, if the injected gas can contain in the small area near injection wells, the performance will be better. And here is the oil net oil production prediction. It says from L04 well, and this is the primary depletion curve, cumulative oil produced, and then this is production enhanced oil divided by Huff-n-Puff. And what the percentage is from 1% to increase to 1.7. So in other words, you have oil production 30 to 70% increase by Huff-n-Puff gas injection. Okay, so that is one project. Now another project conducted by Hayes. What they did is they operated a pilot test using foam chemicals around gas injection. So they used the CO2. So in other words, they used the CO2. They added some chemicals. So when you inject gas, and the reservoir initially had some water there, so then they inject gas and inject some surfactant. They generate some kind of foams. Okay. Why do you want to inject some foams? As I mentioned from previous field test results, so sometimes injected gas will break through to neighbor wells, right? So if you have a foam, so it will mitigate breakthrough problem. Okay, this work done by DOE and the University of Wyoming and using chemical use was heavyweight dull chemical, and so Hayes was the operator. So this test was run for 2 years, and later on, then new Barking wells, new Ross in Montana in the States, new wells. So basically use the new wells, and it builds on the previous experience that he has gained over 2016 to 2018 for vertical well EUR projects. Okay. Now let's look at another one. Is BP project. From BP project of gas and chemical injection, and BHP has 2 EUR projects in Eagle Ford, and one involving gas injection, another one involving the chemical blend. So one is gas injection, another chemical blend. And so then monosyl oil has reported down, also monosyl also conducted a parallel test and plan to do more. So a core laboratory started gas injection in Eagle Ford. These are all DOE projects. Oh, no, I'm sorry. This core laboratory is DOE project. So BHP and Mastering also get a parallel test, but detailed results are not known. Okay, let's talk about analyzing of containment. Here, from this previous project, from this period results shows, and it says if restricted round wellbore is better, right? So what does it mean? That means containment. So what is containment? Contain was contain, this restricted. What is containment? Is it contain the injected gas near injection well. That's containment. Instead of breakthrough far away from injection wells, or breakthrough to the neighbor wells far away from injection wells. So what I found is containment may exist in most horizontal well players. Okay, so in other words, if you have a good performance, you need to have better containment. And so this well have okay, but the problem is some wells like Barking, Eagle Ford, and try the method and find those doing tests have been frustrated by their ability to contain. So field results still shows injected gas, it's easy to break through to neighbor wells. So that is from field results, people found the problem people found out. Okay, so that is the field results, and let me show you. So that is for the now. What I did is so far, because I checked my schedule, some slides for gas Huff-n-Puff I will not present anymore because there's a time limit. I cannot finish all this one. So therefore, I'm going to stop here, and the rest of the slides, I'm not going to present it. So I still have to present gas flooding and water, or gas injection and water injection. So therefore, let's look at this schedule. Next one, I should talk about gas flooding. Okay, I'm going to talk about gas flooding. Okay, first, let me show, first, let me see. Show this one, gas flooding. All right, can you see my new screen now? New PPT's, new slide? Okay, so here we talk about gas flooding. So we use the same model as I did for the Huff-n-Puff flooding. And I mentioned earlier for the Huff-n-Puff, I mentioned that this, this is incremental recovery better than gas flooding. So let's look at the oil saturation map. I also mentioned earlier the oil saturation at 50 years, and here, let's say here in the injection site, oil injection site, oil saturation will be reduced, right? Because more oil has been displaced to the production site. But the problem is, after 50 years, you still have a lot of oil is not produced. So that is gas. Let's look at the pressure. So then there's pressure, same thing. Pressure is injection site, high pressure, and the injection production side is low pressure. Now, after 50 years, high pressure region is still lower than 50% of the area. So that is why. So that is the gas. That is why we again shows gas flooding is not good performance. Oil recovery is low. Now let's look at here experiment data. In this experiment, matrix core probability is 70 millidarcy, and we get velocity is 5.2%. It's 1.5 multiplied by 2, so 1.5 diameter, 2 inches the length, and the initial oil saturation density is 8.7. And see, here's oil recovery, and for different injection pressure. Here is 5,000 injection pressure, and here's 4,000, and 3,000, and 1,000. Okay, so PSI. So what do you observe? What do you observe from? What do you observe from this? What I observed from this slide? It shows the high injection pressure, the oil recovery is high. Okay. And then let's look at gas saturation. So this is time 0.25. This experiment data. Okay. We use simulation model to simulate experiment data, and so the data is here's to match experiment data. Data is simulation data, but here's to match experiment. So we zoom, so which shows the experiment data. Okay. So here's 6.25, 3 days, 5 days. This is basically gas saturation. So red one is high gas saturation, blue one is low gas saturation. So now it's in the beginning, low here, there's no gas injected. So at 0 it's low gas. Now as we inject gas, so now here you start to see the gas. 0. Then as more gas injected, the gas saturation move to right. Okay, move to right. Okay, but then you can see even in this experiment, the 5 days, then the gas starting to move to the production end. So even for such kind of 1.5 inches diameter and 2-inch diameter core, you think about only 2-inch diameter core takes so long for the gas to reach the production end. Okay, so therefore, now let's compare to the Huff-n-Puff versus the flooding. So cup here is half and puff. And so this is the nitrogen. Okay. And here is gas, nitrogen flooding. Okay, because this is flooding. But this is Huff-n-Puff. Its soaking time is 2 hours. And this is 5 hours. And no, 0.5, bottom is 2 hours. Okay, wait a minute. So this one is nitrogen, Huff-n-Puff, 5 hours. This bottom one is nitrogen, 5 hours. And the blue one. This is flooding. So this dotted line is flooding. Okay, now this one, red dot is 2 hours. Soaking time 2 hours. And the top one is 0.5 hours. Okay. Now, what do you see here? Here it says, this is flooding. All right, so this dotted line are flooding. Now, when the soaking time is 2 hours, oil production is similar to flooding. But when the soaking time is shorter, then you have Huff-n-Puff oil production is higher than flooding. When the soaking time is longer, barely 5 hours, actually oil recovery is lower than flooding. Okay, what does that mean? So this data tell us for the Huff-n-Puff, your soaking time should not be too long. If the too long is going to waste the time. And earlier, where our conclusion is Huff-n-Puff is better than flooding, right? But if the soaking time is too long, Huff-n-Puff may produce less oil than flooding. So therefore, from this slide, we can conclude, this slide, the results imply that for Huff-n-Puff, optimization is very important. To get a superior oil recovery performance, the process need to be optimized. So that is what we learned from this work. Okay. Okay, but we did another. We did another test. We used the 400 millidecibel, and its soaking time is 103 hours. Production is 3 hours. Soaking time is 1 hour. And in this case, and we say this is flooding. This is the Huff-n-Puff for 1 hour. Yeah, it's better, Huff-n-Puff better. But let's look at it in the early time. Okay, let's look at the early time. So early time in the beginning, same oil, and later Huff-n-Puff had high oil production than flooding. So this slide shows, so in the beginning now it's very close. Is flooding or Huff-n-Puff is almost the same. But later on, Huff-n-Puff is better. Why? Because in the beginning, when you're flooding, and although all gas has not reached the production end yet, but production side, you have oil there nearby, right? So you immediately produce oil. So therefore, in the beginning, then you see gas flooding can produce oil. So for the Huff-n-Puff, you can quickly produce oil. Why? Because you have a short half period of time, and then you immediately produce. So therefore, now you can immediately produce this oil in the early time. So that is the early time. So therefore, produce oil is close to flooding. But at later time, so for gas flooding, gas breaks through production well. So then you hardly produce oil. But Huff-n-Puff, you could still produce oil by still produce oil. That's why so compared to two methods, so late oil production will come from Huff-n-Puff. All right. So let's give you let me give you some field results. In this field, and reservoir porosity is 7.5, and permeability, matrix permeability is 0.01 to 0.04. And from build-up test, permeability was 2.5 millidarcy. All right. So what does it mean? That means for the field test, so then permeability is higher than matrix permeability. Why? Field build-up test probably you, or maybe you have not known this one. You just probably you have not taken this course yet. But from is field test. Field test shows 2.5. Permeability shows matrix permeability, because matrix did not have fracture, but in the field you have micro fracture, right? So therefore your permeability, the permeability was higher than matrix permeability. Okay, then oil viscosity 0.3, 3 months injection, soaking time, and production time. So it's all 3 months. 3 months production injection, 3 months soaking, 3 months production. And you get a Huff-n-Puff, you get a 2.5%. And then you inject 0.25% gas flooding, you get a 13 to 15% oil cover. Okay, so in this way, let's say injection volumes are almost similar, 0.19, 0.2. But so here, gas flooding get a more oil recovery. Okay, this is something different from what we understand or what we presented earlier. Why? Because in this case, let's look here. Permeability is 2.5 millidarcy. So that means this is a relatively high permeability reservoir. So like conventional reservoir. In conventional reservoir, actually most field project is flooding instead of Huff-n-Puff. So this slide also shows that, also tells us Huff-n-Puff injection mode or production mode only applies for shale or very tight reservoir. Okay. Now let me give you another example here. In this example, we have upper 3 layers and upper 3 layers and low layer, low 5 is 0.05, or viscosity, continuous mode, 4 injector, non-producer, four injector, non-producer. So they tried to use 2 wells for 10 years, Huff-n-Puff, and 2 wells, 5 years soak, and 5 years production. And then rest of the 9 wells are continuous production. So totally is have 13 wells, right? What are the results? They found continuous CO2 injection is better than Huff-n-Puff. Okay, why? That's from field results. So that's the data presented by these authors. Then this is result is against our conclusion, because our conclusion says Huff-n-Puff is better, right? But why their data did not show that? So therefore, I analyzed data. What is the problem? First, obviously, they have 5 years soaking time. Now, I guess from my lectures for today, you should understand, I mentioned several times, and now you're convinced by field project. What is that? soaking time should not be too long. If soaking time too long, Huff-n-Puff is not going to work. Okay. Another thing is in the Huff-n-Puff mode, 9 wells is continuous injection. Only 4 wells Huff-n-Puff. So more than half of the more wells actually in continuous injection. Only small portion of only 4 wells actually in Huff-n-Puff. So therefore, overall production cannot be only from Huff-n-Puff performance. Okay. So another thing is, look here, half K is high for continuous. Let's say half K. Let's say upper layer, you have 2.5 millidarcy. This is the same as the previous example. It also shows if the permeability is too high, Huff-n-Puff performance may not be good. Okay, here's another one is barking formation. So barking formation, and here is 3 horizontal well and parallel each other, produce first 450 days natural fracture matrix, 300 nanodarcy, and let's say continuous central wells use the use the injection well for 1,000 days. And then Huff-n-Puff mode only in the central wells. And then puff 60 days, soaking 10 days, then produced 100 days. Okay, so only in these 3 wells, only 1 well is Huff-n-Puff. 2 other wells just continuous injection. What I found is continuous injection is better than Huff-n-Puff. Okay, again, against our conclusion. Why? Because 2 side wells were not in Huff-n-Puff. This is continuous mode, and 60 days injection is not long enough because you have such kind of area. You only have 1 well in just 60 days, and you have 3 later on. You have 3 well production, and for 100 days, so your injected gas volume is not enough. That's the analysis. Okay, so the reason I want to use counter examples to explain why Huff-n-Puff is better. Actually, I use another angle to explain Huff-n-Puff is better. In some cases, if you find Huff-n-Puff performance is not as good as continuous or gas flooding, so you need to explain why. You need to analyze. It is not because Huff-n-Puff does not work, because in some cases, Huff-n-Puff should not be used in high permeability reservoir, first thing. Second thing is, when you use Huff-n-Puff gas injection, you need to inject enough gas, which I had a patent for that one. I will not go into, I do not have time to talk about more details. That's kind of too advanced topic. Okay. So now let's look at the field gas flooding performance, because in this section we talk about gas flooding, right? So here's a field, different field, and we had a performance, oil rate increased, oil rate improved, some oil rate increased, and let's say what is you just use the gas, lean gas, natural gas, CO2, okay? And here is like permeability 0.1, 0.79, 0.96. Let's say all this project is permeability is kind of millidarcy range. But shear, when we talk about shear permeability, is about a nanodarcy range. So that's why. So that's why I explain here for the gas flooding in the works, because permeability is about millidarcy range, and because if permeability is large enough, then no injectivity issue. Okay, so that is gas flooding. Here's another case. Another case for gas flooding, and they proposed what kind of reservoir we can use gas flooding. So oil plus is about at least $40. Gas price 2.5 MCSCF. Matrix probability less than 0.3 is not recommended. Okay. So for 0.03, 0.1, could use nitrogen. If greater than 0.1, use CO2. And 0.1 to 0.3, and using nitrogen could be economic, but 0.01 to 0.3, and you could use a CO2, right? But CO2 is not economic. So this is a little bit give you some idea what kind of reservoir condition gas flooding may work. Okay, so then it's a good time for me to just finish the gas flooding. It's good time for me to stop here today, and so let's review how far we have gone. Come back to this. Come back to this our schedule. Let's share this one. So far we finished the gas flooding, and we should have finished the water flooding today, but we will continue tomorrow, and we'll continue tomorrow. Okay. And thank you very much for your patience. I know this kind of is a long day. It's long hours for students. So, if you have any suggestion to improve my teaching for this course, because under such kind of environment, let me know. Okay. Thank you again. Okay. Bye bye.